I'd like to talk about one of my research work entitled "The Synthesis of Ion-Based Nanoparticles and Their Assembly for High-Frequency Application in Gigahertz Range." Our final purpose is to fabricate some bulk-style assembly structure for high-frequency antenna devices. This is the outline of my talk. After introduction, I'd like to show my results are two different kind of experimental system and investigation system. One is a non-uniform dipole interaction field system. This means a wild distribution of magnitude and random direction of dipole field interaction between nanoparticles. The other one is a uniform dipole system. This is for the narrow distribution of magnitude and unidirection of dipole interaction field. That means the columnar structure ion nanoparticle assembly. And finally, I will summarize my talk. And my purpose is to fabricate an ion-based nanoparticle hybrid material for high-frequency devices, such as antenna devices. In such devices, device materials, low eddy current loss and high resonance frequency FR and high permeability are needed. In this case, single domain size less than 20 nanometers is needed. And for high frequency resonance to high effective field, that means high effective field directly connected to the magnetic resonance frequency FR. And we have to consider Snooks's limit like this equation, and the permeability and the magnetic resonance frequency is sorry, it's expressed like this equation. That means for high frequency use, high saturation magnetization is needed. So for satisfying these properties, we have proposed the ion nanoparticle assembly like this picture. This is a magnetic nanoparticle, ion magnetic nanoparticles surrounded by surfactant. And for example, this kind of two black powder nanoparticle and white powder polymer compressed like this way, and then we touched on some high-frequency device on this material. In this material case, a non-contact among nanoparticles and that realize the high resistivity and small size less than 20 nanometers with single domain size and high saturation magnetization, and realize high permeability and strong dipole field between nanoparticles leads to provide a high effective field that realize a high magnetic resonance frequency. And magnetic dipole interaction, you know this kind of two magnets between we consider the this kind of nanoparticles. In between nanoparticles, magnetostatic dipole interaction is important factor to determine the behavior of magnetic nanoparticles. And the energy term is anisotropy energy term KVP plus dipole field interaction field energy, like this equation. And between nanoparticles in assembly, we can simply calculate the simple cubic case and the phase-centered cubic case and the similar equation of the magnetic dipole interaction field energy. And the rho is the density of the atoms. And using this kind of magnetic dipole interaction field, we can expect the different kind of magnetic state with as a function of volume fraction of materials. And in a thinner volume fraction case, we can expect a super paramagnetic state like this way, and the nanoparticle moment of magnetic nanoparticle rotates this and that by thermal agitation. And with increasing the high volume fraction case, super spin glass or super ferromagnetic state can be realized, can be expected. And in these cases, dipole interaction field energy is comparable or more to the magnetic anisotropy energy. And we have to effect of this kind of interaction and interaction of magnetic property of alpha ion nanoparticle case, alpha nanoparticle assembly case with well controllable volume fraction. So our purpose is to firstly control the dipole interaction field in the ion nanoparticle assembly. We investigated two cases, non-uniform dipole interaction field system using the alpha ion and gold nanoparticle mixture assembly case. And the other one is the uniform dipole system cases with using the columnar structured alpha ion nanoparticle assembly. And now next item is a non-uniform HDIP system. And we, for investigating the well-controlled nanoparticle assembly cases, and we have some technical problems to fabricate and realize the well dispersion state of nanoparticle. What is the well dispersion state? And former research, we investigated solution system of the nanoparticle. Solution system of nanoparticles, simple freezing process. After the simple freezing process with well-known volume fraction, but unfortunately, when freezing process and magnetic aggregation and inhomogeneous aggregation is occurred, that depends on the melting point of the solvent. So with this is a temperature dependence of magnetic susceptibility as a function of with various volume fraction. Very, very similar case, we can see the blocking temperature here as a blue data. But a little bit with increasing the volume fraction, rapidly increase the blocking temperature we found. But this, I think this rapid increase originates from some magnetic aggregation inside the solution during the freezing process. And also, we have another problem, dispersion in polymer matrix. SiO2 shell coating of, we have to apply the oxidation of the surface of alpha ion particle cases. So we have to propose a new fabrication method. And we have proposed one of the new fabrication methods named the Simultaneous agglomeration method. This method has have some technical merit, easy to fab, easy control of volume fraction and high volume fraction, minimal oxidation and a high melting point. Simply saying, this kind of two different well dispersion state of nanoparticle solution for this, in this case, alpha ion nanoparticle case and gold nanoparticle case, and the mixture with desired volume fraction with each other, and then polar solvent is added into the solution and rapidly coagulate with each other, and then dried out the solvent. We can get some granular alpha ion and gold nanoparticle granular structure we can make. And all of the process in this agglomeration method, we usually do this kind of process in the water and oxygen-less condition under in the glow box, and the preparation of iron precursor and heating at 30 to 130 degrees C for several hours, and then since this iron nanoparticle covered with surfactant, since its temperature is 180 degrees C for 1 hour, and then washing out the impurity, wash out the impurity, and the preparation, the characterization sample. All of this procedure is done in the glow box, very few impurity level, less than 1 ppm. And this is the experimental procedure of the simultaneous agglomeration method. After the synthesis nanoparticle, we can get this kind of nanoparticle. For iron nanoparticle case, average size is 8.7 nanometer, and the gold is a 10.8 nanometer, like this way. And the dispersion state in hexane, hexane solvent, like this way, and for gold and iron, respectively. And mixture with each other, and then addition ethanol, and we can collect the granular structure of particle by magnetic collection. And next, I'll show you the some results of TEM picture of alpha gold nanoparticles granular structure and the elemental mapping with different size. With different volume fractions, 3.8 and 11.3 volume fraction. And black color is corresponds to the gold, and the gray color is alpha iron. And we can see from the mapping, elementary mapping, we can see the gold and the iron nanoparticles separately exist and randomly exist in the this kind of granular structure. And we can control this kind of technique from 3.8 or less volume fraction to maximum is around 40%. And the highest volume fraction of 43% of nanogranular structure is like this way. And this is iron, pure iron. All of the nanoparticles is iron nanoparticle. And from the FFT analysis of this picture, we can get some interval around 8.0 nanometer. That means cross-backing structure of alpha iron nanoparticles, like this picture. And this is AC susceptibility of the granular structure with various volume fraction from 0.5 to 1.6, 4.5, 11%, and 23%, like this way. And this is a real part and imaginary part. Like take a peek, like this way. And we replot the temperature dependence of susceptibility and the phase delay. Like this way, as a function of volume fraction of iron nanoparticles. From this result, with increasing the volume fraction, blocking temperature, like here and here, is increased. And also the peak delay, the phase delay also shifts to higher temperature with increasing the volume fraction. That means blocking temperature increase from low temperature to higher temperature, and that means enhancement of the dipole interaction field in addition to the magnetic anisotropy energy. And this is the hysteresis loop of the granular structure with different volume fraction 4, 6, 16, and 42%. And within the right side shows the volume fraction dependence of coercivity and residual magnetization. And from this result, we can see the drastically decrease of the coercivity and the residual magnetization with increasing the volume fraction. And this, we think this kind of behavior, drastically decrease behavior, corresponds to the collective magnetic behavior. That means some alpha iron nanoparticles simultaneously behaves, rotates or switching, and this kind of behavior is observed. And further investigation, and we investigate the effective field inside the nanoparticle granular structure. How much is the effective field inside nanoparticle assembly? And we investigate the Q-band to FMR spectra at room temperature with different kind of volume fraction. Very thinner volume fraction case, very sharp FMR spectra we can observe. And with increasing the volume fraction, very broadening, spectra is very broadening. And this is replot the delta H. Delta H is defined as a peak-to-peak width of the field. And we replot here this parameter to the volume fraction. And the magnetic dipole mean field is defined like this equation. And we can obtain 2 kilorset around 40%. And this is comparable to simple calculation of the dipole magnetic interaction field between nanoparticles. And also we can estimate the damping factor alpha defined by this equation, 0.02 from the very thinner one to the 0.22 for the maximum volume fraction case. This higher damping factor behavior is very unique property of the nanoparticle assembly cases. And even now, so we have to why such kind of behavior is happen, and still open question. And we also calculated the dipole field inside the nanoparticle assembly using a LLG equation. And we assumed the sphere configuration of nanoparticle assembly like this way. And the blue sphere express the iron nanoparticle. And yes, and we estimate the dipole interaction field. We estimate like this way. And very interestingly, dipole interaction field is very becomes a wide distribution from 2 kiloset to 4 kiloset, like this way. And this arrow shows denotes the magnetic moment of iron nanoparticles inside the nanoparticle assembly, and the vortex structure is formed because magnetostatic energy, to minimize the magnetostatic energy, this vortex structure is formed in this assembly case. And the mean from the histogram of each dipole field, we can get the 3 to 4 kiloset of dipole field inside the nanoparticle assembly. And we change the parameter process, material parameter with size and volume fraction in this case. And we estimate the net permeability, mu net, and magnetic resonance frequency, FR, as a function of volume fraction and the particle size. At high volume fraction, over 40 volume fraction, and the high volume fraction and 15 nanometer case, we can get the net permeability is 4.0. And the FR also can get a high resonance frequency around 10 gigahertz. And based on these results, we check the size dependence of FR and magnetic susceptibility as a function of the size of magnetic iron nanoparticle cases. The packing fraction is changed by changing the size of nanoparticles. So in this schematic view, like this direction. Yes, and in this case, unfortunately, we can only observe the maximum resonance frequency around up to less than 1 gigahertz. And that means in this system, thermal agitation field, superparamagnetic state is co-mixtured around the 8 nanometer to less than 10 nanometer. So we have to much more bigger nanoparticle size is needed for actively applying the dipole magnetic field inside the nanoparticle assembly. And I'd like to show some short summary for non-uniform HDIP system. And we can control the iron nanoparticle volume fraction in the range from 0 to 43%. And such some magnetic behavior is drastically changed compared to the isolated nanoparticle cases. But unfortunately, in this system, resonance frequency is less than 1 gigahertz, not enough for the high frequency application. And this is due to the I think while distribution of H-dip and some magnetization of ion nanoparticle is not enough to enhance the H-dip interaction field. So, so we changed the mind of the H-dip system and to make a uniform, that means a unidirectional state of dipole field system. And we will make a columnar structure alpha ion nanoparticle assembly. And as I showed you last slides, we can see that this kind of vortex magnetic state is realized inside the nanoparticle assembly. And for assuming the high frequency electromagnetic wave like this direction, for these nanoparticles, the direction of magnetization is like this way. In this case, magnetic resonance is happen at low frequency range. And our target is to response to in a high frequency range. That means the magnetization state is like this direction, to vertical relationship to the AC field. So my idea is to align the magnetization state by using the through a dipole interaction field, and align this magnetization state in all of the assembly state. So we propose the columnar structure of alpha ion nanoparticle assembly for unidirectional state of dipole interaction field, like this picture. And we apply now field for fabricating this kind of columnar structure. We apply the field-induced agglomeration method. Firstly, ion nanoparticle dispersed in a polymer matrix like this way, and by applying aligned magnetic field denoted by H fix to minimize the magnetostatic demagnetization field, magnetic nanoparticle is aligned like this along this direction, and then solidify the matrix. We can get this kind of columnar structure. And the main parameter, process parameter, is the concentration of rho of the magnetic nanoparticles and the alignment field H fix. And the purpose is the realization of magnetic nanoparticle assembly for high frequency magnetic response in gigahertz band. And we fabricated firstly columnar structure alpha ion nanoparticle assembly, and we introduced the demagnetization factor Nx, Ny, Nz for characterizing this kind of columnar structure. And also we investigate the high frequency property and discussed with demagnetization factors. And this is the fabrication method for the columnar structure. Matrix material is a hexatorial content, white powder color one, and black powder is a nanoparticle, and the mixing with each other, and the pressed and molding and at 10 megapascal, and we can get a molded sample like this shape. And then this sample is annealed at 400 Kelvin for 1 hour in H fix. H fix is a 10 kiloricet to 30 kiloricet. And then cooling down the sample, we can solidify the sample and cut this shape 4 by 4 by 0.76 millimeter size to minimize the macroscopic in-plane shape anisotropy. And this is one of the optical microscope image of the sample. And the black colored agglomeration is a ion nanoparticle columnar structure. And the white colored one is a matrix. And inside the columnar structure, we can check the cross-sectional TEM image. And the 3D nanoparticle is aligned 3D or self-organized agglomeration like this way. And we can estimate the volume fraction of iron in the assembly is 51 volume percent. And we investigate the demagnetization factor for each direction of the sample X, Y, Z direction. And very simply saying, in the high field region and the low concentration of iron nanoparticle, realize the unidirectional state of HD. This kind of columnar structure is formed. And because NX is very small along this H-fix direction, the same direction of as the H-fix. And the X and Y, Y and Z parameter is almost same. So very unique structure along X direction is formed around this area. On the other hand, zero H-fix area and high volume fraction case, X and Y, NX and NY is almost has the almost same. That means a random dipole interaction inside the nanoparticle, inside the nanoparticle assembly, like this picture. So we can fabricate this kind of columnar structure within this kind of process parameter. And this is a complex permeability spectra as a, with various kind of process parameter with concentration is 0.9, 0.5 to over 50%, and with also H-fix 10 kiloset, 20 kiloset, and 30 kiloset, like this way. And red data is the experimental plot, and also the blue colored one is a fitted line by using a model angular distribution of internal field. And we can well fit the data under high frequency property for lower concentration and the higher H-fix region. We can get the high frequency response in this sample, in these samples. That means we can achieve the uniaxializing magnetic dipole interaction field. And this is a replot. We replot the FR data as a function of concentration and the H-fix. The color is changed as a function of FR is 3 gigahertz to 10 gigahertz, like this way. And high H-fix and the lower concentration can realize FR, for example, 11.1 gigahertz at H-fixes equal 30 kiloset, and the volume fraction is 1%. And also we can replot the obtained FR data to this relationship, and y-axis is the experimental FR, and the x-axis is the scaling function we modified. And the first term is maximum, express the maximum dipole interaction field inside the assembly, and the Nx and Ny, the difference of this kind of parameter means difference of the dipole interaction field along each direction. And we can fit with scaled with this kind of equation. So FR in the ferromagnnetic resonance frequency can be scaled with using this kind of equation for this kind of magnetic nanoparticle assembly. And also we can estimate the Snooks limit for the columnar structure case. This resonance frequency is expressed in the before slide. And also we can estimate the mu net expressed like this equation. And this is a calculation limit, upper limit for the based on the Snooks limit using this equation. And the experimental plot is like here. Unfortunately, we have to this experimental data is not reach the upper limit for the calculation. For example, but if we can apply this kind of if we can realize this kind of ideal state, we can get the much more high frequency response and high permeability. For example, iron cobalt nanoparticle cases with high saturation magnetization, we can get net permeability 2.0 and FR resonance frequency is over 10 gigahertz, around 15 gigahertz. Finally, I showed summarized my talk. We investigated two kinds of different nanoparticle system, and up to the present, my answer is not enough for to apply to the real application. But from now on, iron cobalt high saturation magnetization is, I think, iron nitride is one of the key issues to enhance the high frequency properties. Thank you for your attention.